Okay, I think we can start. It's a great pleasure for me to announce the next plenary speaker, Alexander KURGANOV. He has done his PhD in 1997 in Tel Aviv, and now he's a full professor in Tulane. And he's going to talk about Central-Upwind schemes for shallow water models.
Okay, so I would like to thank the organizers for inviting me to give this presentation at the Hyperbolic meetings. And I will talk about Central-Upwind schemes for shallow water models. So I don't list my collaborators because it will be based on many different works, and I will mention my collaborators during the talk. So shallow water equations, probably in this audience I should skip this slide. They obtained from depth averaging of Navier-Stokes equation in the case when the horizontal length scale is much greater than the vertical length scale. And there are many books where you can read about the derivation of shallow water equations, but I would like to mention this work by Gerbeau and Pertencem, where it is done in a rigorous way. So shallow water equations are used in a lot of for different applications, so to model flows in rivers, channels, lakes, coastal areas. It is used in oceanography, atmospheric science, and so on. So they're also very important for hydraulic engineers, for coastal management. And let me move on. So this is the setting, the simplest setting. So I will talk about the simplest shallow water equation, and then I will start adding some terms that will make them a little more challenging. So this is the setting. So this is the bottom topography, which I denote by z of x. The depth is h, and the water surface w, which is z plus h. And the system, the Saint-Venant system, in 1D, it reads in a very simple way. It's a 2x2 system of balance laws. In the case when z is flat, it will be just system of conservation laws. And one can write it in a vector form here. So h is, as I mentioned, is a water depth, u is a velocity, q is a discharge, and g is a gravitational constant. So what I'm going to talk about, numerical methods, and I will, just to introduce the notation, so I'll talk about finite volume methods. So if I consider a general system of conservation laws, again 1D, so I will show 2D results, but all techniques and everything I will present in 1D. It's good enough to explain the ideas, and 2D, it's just takes more time to do algebra, and the notations are longer, but the ideas are more or less the same. So in finite volume methods, the quantities that are evolved in time, these are cell averages. So I introduce the cells, Cj. This is the cell. So in every cell we have the center of cell is xj, and the cell boundary is xj minus a half, xj plus a half. So as usual in finite volume methods, given the cell averages, they're used to obtain piecewise polynomial reconstruction. This Pj, which is supposed to be conservative, or I said second order, actually high order, depending on the order of the scheme, and it's supposed to be non-oscillatory. And for example, for the second order schemes, we need to have piecewise linear reconstruction, which looks like this. So the only degree of freedom is the slope, and the slopes, they're supposed to be obtained to make it non-oscillatory using some nonlinear limiter. For example, the mean mode limiter, that's the one which is used in all of the examples that I will show you, but other limiters can also be used. So when the slopes are available, one can compute the point values, and at each cell interface we have 2 point values, which I denote u minus and u plus, because at the H cell interface we have 2 pieces from the J cell and from the J plus first cell. So we have 2 cells, and generically these 2 values are different. So here is a typical situation of this reconstruction. So at every time when we are ready to evolve a solution, at each cell interface there is a jump, and these jumps, there's some waves starting, because we consider this as an initial condition, and then there are waves that are generated at these cell interfaces, and one can estimate the speeds of these waves using the largest and smallest eigenvalues of the Jacobian. Obviously, for the shallow water, it will be just lambda 1 and lambda 2, and this will be u plus minus root of gh. Okay, so I will not show you how to derive Central-Upwind schemes because I want to spend more time on, or I want to focus on numerical method for shallow water equation. But Central-Upwind schemes, that's a type of Godunov type central schemes with some built-in upwind nature, and we have derived them in several of works, and starting from 2000, that's a paper with Eitan Tadmor where we started this business, and then we continued with Gergana Petrova, with Sebastian Nolli and Gergana Petrova, and then the latest out of published works on Central-Upwind scheme, it was my paper with Etienne Lin from 2007. So what I will do, I will write this as a magic formula in this lecture, and once again, the derivation, maybe that's the recent paper is the best to read if you're interested. So the scheme is it's a semi-discrete scheme. So to obtain fully discrete, one needs to use an ODE solver. I write it in the flux form. So this is numerical fluxes capital H, obtained from the physical fluxes, and these values of u plus, u minus, a plus, a minus, which I introduced. So this is a scheme for a general system of conservation law. So what we like to say, because there's no Riemann problem solver involved. So this is just a general recipe. It's a black box solver for a system of conservation law. So what I need to know the eigenvalues, and actually I don't even need to know eigenvalues. I just need to have an estimate on the largest and smallest eigenvalue. Okay, so yeah, just a small remark that if this term here is 0, then it reduces to the Central-Upwind scheme that we introduced with Nolli and Petrova. Also for system of balance laws, because shallow water is always the most interesting situation when the bottom topography is not flat, so we need to deal with the source terms. So if I have a source term, so the thing is that with central schemes, the fluxes are fixed, and the only degree of freedom is how to compute the average of the source. So basically, that's the only thing we need to do, and then you have the scheme for the system of balance laws. Okay, so the 2D extension of Central-Upwind schemes is just one slide. So it has been done in both rectangular and triangular grids, and this is also a list of papers. So for triangular grids, we wrote the paper with Gergana Petrova in 2004. So now back to San-Venant system. So there's several numerical challenges, and they're related to steady-state solutions. So if I write a steady-state solution, these are smooth steady-state solutions. And a particular steady-state solution is lake at rest, which is here. It is obtained from this set of solutions in the case when the velocity of the discharge is 0. Why steady states are important? Because in applications, a lot of waves which are to be captured numerically, they are just small perturbation of steady states, and the method should be able to preserve steady states, because otherwise the numerical errors may be larger than the waves to be captured. And the method may be not useless, but one will have to use a very fine resolution to capture physical waves and to avoid the situation when numerical errors are larger than actual waves. And this fine resolution may be unaffordable. In 1D, probably it is always okay, but in 2D, it's very easy to get into the situation where errors will be too large for any practical purpose. Another challenge of the San-Venant system is the situation of dry states. Actually, when the San-Venant system is derived, they assume that H is always positive. However, in reality, you have to deal with these situations when you have shores, islands, and so on. So we do need to deal with this, and the numerical scheme should be able to handle situation of very small h or even h equals to 0. So let me give you a brief review. It's actually, there has been enormous amount of activity on numerical math for shallow water, but there are some milestones, and let me start with Randy Leviak's paper, where he incorporated the source term into the Riemann solver. This was the main idea. Then Shijin in 2001, he proposed a source term averaging, this well-balanced averaging for the source term that helps in many, many situations to design the scheme which is well-balanced. Well-balanced scheme, so that's the first time this word appears. It's the scheme that is capable of exactly preserving steady states. So if you plug in the data which correspond to steady state, it will be preserved by the scheme. Not within the accuracy of the scheme, but will be preserved exactly within machine accuracy. Okay, because within the accuracy of the scheme, then any reasonable scheme will do this. Pertencem and Simeoni, they developed kinetic schemes. Then we developed the Central-Upwind scheme back with Doron-Levy in 2002. I wanted to mention the work of Galloway and his collaborators about the row-type schemes. They call it VFRO schemes. This is another milestone of Odus, Bouchot, Bristock, Line, and Pertencem, when they introduced the hydrostatic reconstruction. It is a very popular technique to make scheme well-balanced. Staggered central schemes were proposed by Giovanni Russo. Then Wiener scheme, no, I need to go back. Wiener schemes were developed by Xin and Shu in several works. Higher order schemes, well-balanced schemes were proposed by Nolle, Pankratz, Pupa, and Natwig. Then the finite volume evolution Galerkin scheme that Maria Lukachova, who is here but not in the room but in this conference, with Nolle and Kraft, and relaxation schemes by Berton and Marsh. This is also, there was a talk by Christophe Berton about this work. So this is partial list of some people who I did not include here, but they contributed a lot to shallow water equations and with the recent works. This was well-balanced scheme that preserve lake at rest steady states. So it's trickier to preserve moving steady states when U is not identically 0. So here I mentioned several schemes where this has been done, several methods. And among the schemes that I mentioned on the previous slide, there are schemes that also preserve positivity, including some new techniques here which were obtained by special space-time quadrature by Bollerman, Nolle, and Lukachova. And I also contributed, we worked on this wet-dry front, and we obtained special reconstruction of wet-dry fronts. Okay, so but I will focus on Central-Upwind schemes, and our goal is to design the method which is very robust. That's what we like, because in reality, you not only solve the Sandman system, but you have to have additional terms that model friction, viscosity, Coriolis forces, temperature variations, dispersive terms, and so on. And Central-Upwind scheme, like other central schemes, being a black box solver, which is also quite accurate, or I would say highly accurate, makes it attractive to many practitioners. It's even used to predict flood, to do flood management, flood mitigation, used by many U.S. federal agencies. So the system was developed in the National Center of Computational Hydroscience Engineering. So this is a very sophisticated tool that I learned about this last year, that they used the Central-Upwind scheme. Okay, so how to obtain the central? I said the only thing is how to discretize the source, and this is the source. So what we did with Doron-Levy back in 2002, we first rewrote the system using this water surface variable instead of h. These systems are equivalent. It is actually not really necessary to rewrite the system. It's possible, but not necessary. It's convenient, but not necessary. What is really important that the lake at rest steady state, the variables q and w, they're constant, and these are equilibrium variables, and we need to make reconstruction for the equilibrium variable. That's what is important. And how to design this quadrature? In framework of Central-Upwind scheme, we do it the following way. So we say here's the steady state. This is the flux. And what we do, we take the steady state data and plug it in, not into the flux, but into the numerical flux. And it happens that the numerical flux of the Central-Upwind numerical flux will be identically equal to the physical flux. And then the contribution of the fluxes in the evolution of the second component of the discharge will be this. So then we look at the source, and we need this expression to be 0 at the Lake-Atrex steady state. This dictates what quadrature one should use to make the scheme well balanced. That's very simple. And that's what we did. And now I would like to move on and to add another feature. I want the scheme to be positivity preserving. So to make the scheme positivity preserving, that's what we did with Gergana Petrova in 2007. So there are several steps needed to do this. First, the bottom topography. So instead of having this function, brown function, okay, it's just some function. So we replace it with linear piecewise continuous approximation, as it is done on here. So the black curve. So we just take the values of the bottom topography at cell interfaces and connect them. Okay, so that's the first step. The second step, we need to make positivity preserving reconstruction of the water surface W. So why do we need this? Because in some places like here, or I can, yeah, this is here's a more local picture. Let's say this is cell J. This is a value of Wj, which is above Zj. So it's a positive. The average amount, the amount of water is positive. However, the reconstruction, even the piecewise constant reconstruction, the first order one, may create the negative values of H. It cannot be avoided by any limiter or anything like this. So after you use the limiter, your favorite limiter, the mean mode or anything else, you need to correct the reconstruction. That's how we do it. So we rotate it until it reaches the situation that there's no negative values. That's what we did with Gergana Petrova. And after this, the reconstruction will not produce any negative values. And once again, it is important to have the bottom structure to be linear, because in this case, we can guarantee that everywhere the value of W minus B, which is H, will be positive. And the third step, it is very important, but it is often in the papers, people don't mention this, but this is really important, and a lot depends on how you do the desingularization. When you compute U, it is Q over H, but for small h, this does not work. For h equals 0, this is not defined, but even when h is very small, it's dangerous to do this because U may be artificially large, and the time step will be very small, and the scheme will not work. That's the issue of robustness, comes here a lot. So the simplest thing is just to do this cutoff and say U is 0 if h is too small. There's some smoother version, more sophisticated, smoother transition for small h, which I write here. There are two options, and they have advantages, disadvantages. It is important to understand that no matter what you do, the desingularization is so important that it may kill the robustness of the scheme. And in fact, for many situations, you have to tune this desingularization parameter. You have to play with this to obtain a good result. So to the best of my knowledge, there was someone in Madison, Wisconsin, who tried to systematically design some, but I don't remember who it was actually. But I don't think that the results were ever published or ever obtained. So this is the issue which is very important. But no matter how you do the discretization, for consistency, you have to recompute the discharge by multiplying H by U. Okay, so after these three steps are made, so then what we can prove that if the SSP ODE solver is used, strong stability preserving ODE solver is used, then the new water height will be a linear combination of the reconstructed water heights. All reconstructed water heights are non-negative, and the coefficients alpha will also be non-negative, even positive, if an appropriate CFL condition is satisfied. And in 1D, the CFL number is 1/2, which is the same number as for central schemes. For 2D, it reduces in the Cartesian case to 1/4, in the triangular mesh to 1/3. Another important thing, very important practically thing, because when you use, this would be good for forward Euler, which is the first order strong stability preserving ODE solver. If you use higher order, then adaptive time step control has to be implemented, which means that if after one step of forward Euler, of SSP, you realize that delta t, the new delta, not the new delta t, but the second stage of SSP solver, you usually do not check what delta t should be, but you have to check. And if it is larger, if it is smaller than the original delta t, you have to reject the time step and you have to use a smaller delta t. This is very important because this caused a lot of trouble, and it's actually thanks to my PhD student that we learned about this, because we had a lot of trouble with time stepping before we realized that this adaptive time step control, that it is very important. So let me show you some examples how the Central-Upwind scheme works. So so this is small perturbation of steady state. Let me show it here. So this is initial data. That's the bottom structure. It goes all the way up to the top, and they have some oscillation. And that's a bottom structure. And that's a perturbation, small perturbation that splits into two parts, and the one that goes to the right goes over the hump. And if the scheme is not well balanced, you see a lot of oscillations. And that's on a certain grid. If you take finer grid, the oscillations are smaller. If you keep refining the mesh, you see that the results are identically the same, but it's really on a very fine mesh. That's what I meant when I said that the well-balanced schemes are, it's a matter of resolution, which in practical situation, it will be unaffordable. Okay, another example where we have a Riemann problem and over discontinuous bottom. When the bottom topography is discontinuous, the problem, this Sandvenant system, becomes much more complicated. I thought of talking about this, but because of the time limitation, I will not talk in this presentation, but I wanted to stress that the case of discontinuous bottom topography should be studied very seriously, and with the Central-Upwind scheme, we simply replace the bottom topography with piecewise linear approximand, which is continuous anyway. But in some situations, that's not the best thing to do. That's what I will say. But in this example, it works nice. That's a solution. Okay, I show the solution on two different grids. There's very nice convergence. And you see here there's some dry area with discontinuous. So, okay, it works. Another example where I take the Sandvenant system and I have to add friction for convergence to steady state, and I add friction from Gerbois and Pertam paper, and this formula is terrible, but here it is. That's the bottom structure you see here. I assume that there are three dams at the left, on the right, and at x equals to 0, and then there's a dam break at x equals to 0. That's the initial time, and then the water starts flowing onto the right. You see it gets up to the end, reflects, and in time it converges to the steady state, which is quite complicated. It has dry areas, several lakes, and the scheme works pretty nice. It's pretty robust here. So for 2D, again, I said that I will not write any formula because it takes time to introduce notation and so on, but we did this in Cartesian grid. In both the papers with Ron Levy and Gergana Petrova, then on triangular grid on a more recent paper with Bryson, Epstein, and Petrova, and a very recent paper which we submitted just 2 months ago. We extended it to polygonal cell vertex mesh. These guys, Mohammedian and his PhD student, they're engineers, and they really solve practical problems. They need to design tools, and they prefer such meshes. So these are polygonal meshes which are based on first you do triangulation, and then you connect centers of triangles and obtain these polygonal meshes, and we extended the Central-Upwind scheme to this type of mesh. Let me show you some 2D results. So this is, by now, it's a classical problem proposed by Randy Levesque, where we have some elliptical hump, and there is a perturbation, again, small perturbation. which propagates to the right here. So originally the perturbation is here, then it propagates to the right, then it goes over the hump, and you see how it interacts. So what you see on the left, that's a well-balanced scheme. And on the right, that's an example of non-well-balanced scheme, and you see how many parasitic waves are. And for later time, you see that this is a structure, this is a well-balanced scheme, and on the right, you see non-well-balanced scheme. It creates some waves that have nothing to do with reality. And in 2D, it's very hard to achieve a nice result with mesh refinement because it's expensive. I will show two more examples. So here, the first one is a small perturbation. The same thing, it goes over the submerged flat plateau. And in the other example, it will be the island. Okay, so, and then when it goes over the plateau, you see on the top, it's the sequence of times, and this is a well-balanced scheme, and this is a non-well-balanced scheme. So you see, even before the perturbation reaches this area, so some oscillations start developing, and you see the structure of the solution is bad for the non-well-balanced scheme. And in the case of the island, so here we have the small perturbation that bends around an island because the island is too high and the perturbation doesn't go over to the top, it just bends around. And you see the well-balanced result, the non-well-balanced result, and non-well-balanced results are clearly bad because near the islands there's some waves that start propagating and they destroy the solution structure completely. So now I will start adding some terms, and I will start with the friction term. So I will not add the friction term from the Gerbo and Pertam paper, but I will add the Manning friction term, which is considered to be the most popular among engineers or practitioners. So this is a Manning coefficient, and then I also add some rain source because I will talk about some problems where there's a drainage, rainwater drainage in urban areas. So I will get there very soon. And this is my joint work with Alina Chertok, who is in the audience, and two of my PhD students, Shuma Tsui and Tong Wu. So first of all, when we add this Manning friction term, we still have lake at rest steady state. But there are some other simple but very important steady states which one has to study. And this is the steady state, which I call non-trivial steady state, where Q is constant, H is constant, and the slope of the bottom is also constant. So to avoid any algebra, it looks like this. Okay? So in practice, obviously, the slope is not constant, but the scheme has to preserve this steady state to deal, to nicely deal with the water that goes away from a certain slanted surface. Okay, and this will be the urban area that we will consider in the more interesting 2D case. So how we design the scheme? So we use the same ingredients, replace the bottom with a piecewise linear approximation, correct reconstruction, regularized solution, and use well-balanced quadrature for the geometric source term. Now, how to treat the friction term? In fact, with some other methods, it's maybe complicated. With the Central-Upwind scheme, we just use the midpoint quadrature, and it results in a well-balanced scheme that preserves this type of steady state, not only the lake at rest. Okay, so another ingredient, when we correct the reconstruction, instead of doing this, as we did in the original paper with Gergana Petrova, we have to do it a slightly different way. So, and this alternative, I wouldn't say that it's better, or in general, when you do the correction, you may do it in any way, as long as your correction is conservative and you do not create any negative values. So here, we simply made the slope of the water to be equal to the slope of the bottom piece. This was important for this type of applications because we consider the bottom with a constant slope. And here, how the small perturbation goes away, that's a supercritical case, and this is a subcritical case, so it works nice and clean. So for two-dimensional examples, so I will take something very practical. So we consider this rainfall runoff situation on the 2D surface with houses, And actually, we took the laboratory experiments, which was provided by Louis Serre to us, and they constructed the model, the lab model, 2 by 2.5 meters, and they put some blocks instead of houses, obviously, and they poured the rain uniformly, and this is the structure of the bottom, and then we add houses. There are different configurations. That's a direction, so this is houses now in the horizontal direction, vertical direction, or in the mixed way they put. And houses are obviously added to the bottom topography. And one could use just directly the shallow water system with the Manning friction term to simulate this. So, okay, we take this is initial data, it's almost dry initially. This is a source of rain, uniform, and it stops at time either 20, 40, or 60. There's 3 experiments that they conducted. And they measured the outlet discharge because the water here, that's the lowest part, and the water will go here. And they measure the total discharge at the lower part of the domain. And a comparison with the experimental result is not bad, but in some areas it is the agreement with the experiment not so satisfactory. So we came up with additional tool which was important and very simple. And here we really remember that shallow water model, shallow water equations are not good when h is very small. What happens over these houses, that the height of the houses is much larger than the depth of the water when rain comes. So it's not a good model. So instead of dealing with the houses, we replaced the domain with a punctured domain. It's a rectangular domain with puncture. We removed the houses. We made them like solid walls here. And we looked at the areas near the houses, and we redistributed the water that falls, rainwater falls onto the house, onto this area along the houses. When we did this, the results, so okay, we increased the source near the houses, okay, in the shaded areas. And then the results, you could see the much better agreement. So as we joke, our results are better than the experimental results. Because in the experimental results, this model was not stable. That's why you see a lot of noise in the experimental results. So they say the experiment actually modeled the rain over the urban area, but it is rain that comes together with earthquake, which is not always the case. So these are some just snapshots of the water height in the different configurations. So you see, in this case, the water goes away. In this case, there are houses that block the water. Some lakes appear behind the houses, and this is the other configuration. So the next terms I would like to add to shallow water equation and to show you how to treat them. These are Coriolis forces. Coriolis forces, once again, it looks very simple because it does not damage the presence of Coriolis forces here. These are 2 terms. Still, the lake at rest steady state is preserved, so you can use the scheme as it is. You can use some midpoint quadrature for these guys. But in the case of the Coriolis, presence of Coriolis force, and these are usually oceanographic scaling, the lake at rest steady states are physically irrelevant, and one has to deal with other geostrophic equilibrium. And here are steady state solutions which are physically, lake at rest are not interesting. These are interesting. And these are steady states, so which are written this way. So U is constant, V is independent of Y, H is independent of Y. The bottom structure should be also independent of Y. And K is a constant. What is K? K is G times H plus Z, okay, minus V. And V, this is the K and L, they're potential energies. And this V, it's a, roughly speaking, antiderivative of little v, of the velocity, this velocity v. And the same thing, capital U, it's antiderivative, but in the other direction. So here you have to deal with equilibrium variables which are globally defined, not locally. And we need to make sure that these steady states are preserved. So, but I will not talk about 2D. Let's look at 1D. 1D system with Coriolis forces, I still need to consider the third equation for HV. So this is the system, this is the 1D version. And the geostrophic equilibrium will be like just this. U is constant and K is constant. And once again, K, this is a global variable. So the key word, again, it's reconstruction of equilibrium variables. But now it is more complicated than in the case of just standard system without Coriolis forces. So I'll try to explain this. So how we do this? First, we obtain the values of U and V this way or with the desingularization if needed. Then we need to compute this capital V and use just a midpoint quadrature to obtain capital V. This is the integration. And then when we have capital V at cell interfaces, the average of two cell interfaces gives the capital V in the center. Then we can compute K, because K is G times H plus Z minus V. And then we reconstruct these variables, the equilibrium variables, U, V, and K. We reconstruct them. These are piecewise linear reconstruction. And then with this reconstruction, we obtain the reconstruction for H. That's absolutely crucial to design the well-balanced scheme in the case of Coriolis forces. In 2D, it's a little more sophisticated, it's more complicated, but the same idea works. Let me show you just one example. In this case, it will be 2D geostrophic adjustment simulation. So this is the initial data. And we have some perturbation of geostrophic equilibria. So the initial perturbation will generate two circular shock waves. They will propagate outward with a clockwise rotating elevation staying behind the shocks. And this is really complicated problem. And numerically is changing problem. So this is the perturbation. And that's how it evolves in time. This is time 4, 8, 12, and a later time. And the convergence is pretty nice, and there's no parasitic waves that would appear if one uses the non-well-balanced scheme. Okay, so I got to the last part of my today's presentation. So now I will talk about shallow water system with thermodynamics. So that's another additional term. Actually, one can combine this term. I'm just showing you the techniques, and to show the techniques, I try to make it as simple as possible. So in practice, you have to deal with several of these terms together. So what is thermodynamics? So that's the simplest shallow water system in which horizontal water temperature fluctuations were taken into account were proposed by Ripa in these works and later in the paper by Deller. So basically, this system they used to model ocean currents with sharp interface between cold and warm water. So the derivation is quite complicated. It uses multi-layer, and the models that we derived in these papers are really multi-layer shallow water. I don't want to talk about multi-layer shallow water in this presentation. And what we did in the paper with Alina Chertok and my former PhD student Yu Liu, the paper was just recently published, maybe this month. We considered just the simple single-layer Ripa system, 1D and 2D. That's sufficiently complicated. So I believe that the method that we developed can be extended to more realistic multi-layer method, but we have not done this. So this is the simple 1D Ripa system. So that's this is, you see, if I remove the red parts, this will be the Saint-Venant system. But now this is the potential temperature, and this potential temperature affects the pressure and the bottom friction term, and the temperature simply propagates with U, okay, transport with U. So, and again, if theta is constant, then it reduces to the Saint-Venant system. So Christophe Berton in his talk, if you came to his talk, you already saw this system. Okay. So okay, this is a bit repetition of what he had said, but that's okay. So these are the eigenvalues, And we do have a resonance phenomena. And this makes it really, really complicated for, if you want to design the upwind scheme based on the Riemann solver, then they did this, Christoph and Christian Klingberg, they designed a certain Riemann, approximate Riemann problem solver, but this is tricky. Okay, so so steady states. The steady states here, we do not have just algebraic relation as for the Sandvenant system. We have the differential relation, and there are two types of very simple steady states, like at rest states. This one, when theta is constant, this is the same as in the regular shallow water or Sandvenant system. And when the bottom topography is flat, we have another type, I call it type 2 steady state, where both h and theta jump. So how to design the well-balanced scheme? So for the first steady state, so we more or less use the same technique as for the Sandvenant system. This theta does not matter, does not change things, especially since near steady state, or at this steady state, theta is constant. For the second one, it is completely different because this jump, it is really the current, the warm and cold water, there's a sharp interface, and one has to deal with this interface because numerically this interface will be smeared and this will cause a lot of trouble. I will show the trouble later. So we use the interface tracking technique that we introduced with Alina Chertok and Smadar Karni for compressible multifluid. So it worked here as well. So, and that's what I would like to describe more. But first, let me show you the trouble. So small perturbation of steady state. So what I have here, it's a combination of type 2 here and type 1. That's a jump in W. And this is a small perturbation. When it propagates, you see the structure is really bad. It's very smeared here, some oscillation appear. That's if if a non-well-balanced scheme. We have direct application, just non-well-balanced Central-Upwind scheme. So that's another thing, pressure oscillation. That's what resembles the compressible multi-fluid. So here we have the pressure is constant, but h and theta, they jump. So, and if I look at the pressure, which is supposed to be constant, it's supposed, the exact solution will have just constant pressure. But you see the pressure oscillations, and if you refine the mesh, they don't go away. So, again, for type 1 steady state, it's like the Sandvenant system. I don't want to go into there's nothing to add. There's some differences, but I don't want to talk about these details. But I would like to talk a little bit. I have maybe 5 minutes left or something like this interface tracking method. So how do we track the when we have temperature jumps? So we need to first use the level set approach. There are other ways of tracking these interfaces, but we use the level set approach. So this function phi helps us to trace the interfaces. And then when we know that in a certain cell there's an interface between warm and cold water, all cell averages, we say they are not reliable. This is like mixed cell, and this is artificial numerical mixing. We don't trust this value. We throw it away because it's not reliable. But we need to recover these values. We don't have the cell average, but we need the point values. We need to obtain them somehow. And we have two reliable cell averages, and cell j minus 1, cell j plus 1. So what we need to do, we need to interpolate between them. But how to interpolate? We need to go to the phase space, and basically we solve the Riemann problem. We need to solve the Riemann problem with this is the left state, this is the right state, and this will help us to interpolate this. But how to solve the Riemann problem? So we solve it approximately. First, we switch to primitive variables, and we add the force equation for z, for the bottom surface. Bottom topography. Then we introduce the linearization. Okay, that's the linearization about the very simple average states. We don't need any rho, averages, anything like this. But still, this is a linear system. It does not have a complete eigenstructure, so we cannot solve it. But then we use the operator splitting. We split this, this system into two with M and L matrices. This is M and L. And M has complete eigensystem, and for the L, we have just three decoupled linear advection equations. And this helps us to design this approximate solution of the linearized problem. I don't know whether this method is good for evolution, but I don't use this for evolution. I only need this to interpolate between these two states. And the interpolation is done the following way. So I obtain these intermediate values, HL star, HR star, U star, and P star. And this is a contact wave. That's where the temperature jumps. And to obtain the value U J plus half, J minus half plus, which means the value on the left, depending on whether this wave goes to the left or to the right, I take one of these, either the value from J minus 1 or the star L values. And the same thing for the wave going to the right. If it goes really to the right, then I take these values. If not, then I take the value J plus half. This way, once again, I obtain these 2-point values. Okay, I'm equipped with these 2-point values. I can complete the construction of, I can complete the reconstruction in the cells J minus 1, J plus 2. Because I didn't have the cell average here, I could not do any reconstruction before I had these point values. Then we need to trace how this interface propagates. Okay, there are some techniques to make sure that the method is conservative. And this is the interface method. And to end my lecture, I would like to show you some results. So here is the same example that I showed before. You remember this was a bad result. And this is the result we obtain now with the well-balanced scheme. When I call well-balanced, it's a well-balanced that only preserves steady states of type 1. That's the same property that with the method that was presented by Christophe Berton. But if you also introduce this interface tracking technique, then you see the resolution is much, much sharper. That's for W, and this is the P pressure. Okay, so this is the later times you see that interface tracking technique is really important. Here's another example that also Christophe showed, the dam break over a flat bottom. So we have the solution. That's what you get without interface tracking technique. But with interface tracking technique, the contact discontinuity here is resolved really, really sharply, as you can see, and no pressure oscillations. This is a dam break of a non-flat bottom. It's the same thing. And at the end, I'll show you some 2D results. So here it's a steady state. That's the structure of the bottom topography. Yeah, you see here. And once again, if the method is, here one can see, if the method does not incorporate this interface tracking technique, then the contact discontinuity is really spread and you have some parasitic waves. While if you use the well-balanced scheme with the interface tracking technique, then the resolution is very sharp. The same thing happens if I introduce some small perturbation of the steady state. You see here it's nicely propagated, and here it is pretty bad. It's damaged by the artificial waves. And the last example, it's a radial dam break. So we have this radial dam break. The result, this is the well-balanced scheme, but no interface tracking technique. This is a with interface tracking technique. And once again, the resolution of the contact discontinuity is much sharper here on the right, as you can see here. So it's much, much sharper, and you see it here. It's not spread as without this interface tracking technique. So thank you very much for your attention.
Thank you very much for your interesting talk. Are there questions or remarks? Christian?
So in this example, try to stop the that exactly you're getting it
No. Just trophic equilibrium is preserved exactly. It is preserved exactly. The only trick is how to design the initial condition. So you design the initial condition, and then initially, if it is at the trophic equilibrium, it's preserved within the machine accuracy.
Other questions? I have a question. I didn't get the point. If the bottom is discontinuous, what are the details of the discretization in that case?
So if the bottom is discontinuous, so what we do, because the discretization of the bottom, we always replace the bottom with a piecewise linear, continuous piecewise linear reconstruction. Even on this picture, okay, it takes time to get back, just 1 second. Even on this picture, the schematic picture of the bottom, I had the discontinuity. Where was it? Here. Yeah. So I had the discontinuity. Yeah, you see here. But what I do, I just replace everything with a piecewise linear, continuous piecewise linear reconstruction. So in many cases, so this means that when delta x is small, I will have very sharp gradient. But it will be still proportional to 1 over delta x. In many situations, it works fine. However, there are situations where additional techniques should be used, but it goes beyond the scope of this talk. So basically, when it does not work, I would say that then the Central-Upwind scheme fails, and one has to design, we're working now on this, on the Central-Upwind scheme with the bottom topography without this piecewise linear continuous reconstruction. So then several additional techniques, including past conservative scheme that we designed for this, and this average that Shijin has proposed. I didn't have time to talk about this, but it is much more complicated. But in some cases, or let's say in most cases, it's not needed. So in most examples, we just did this, and it worked. So we replaced the jump with the continuous. Oh, we have done this in 2D. It is really more complicated because it's not always that we have one cell, and so you need to consider several situations. And roughly speaking, for every cell which is a mixed cell, what we do for neighboring cells, we need to have, if we don't have reliable data, we need to extrapolate it or interpolate it from nearby neighboring cells. So if everything is, if the interface is really like this and no good cells around, it means that just the resolution is, it's too, the grid is not fine enough, not refined. And you cannot design the method that will work on any grid, because you need to refine the grid if the interface structure is too complicated. However, for a reasonably complicated interface structure, we have the method and it works. We designed it for compressive multifluids and it worked. I showed the results. So we really, in shallow water, we did not consider too complicated. But with the compressive multifluids, we consider a situation when a shock hits a bubble and very complicated structure of interface, and it is capable of, but once again, in some situations, without mesh refinement, it will be impossible. But here, it was fine. And the extension, it is in the paper, we describe this, how to do this. It's a bit, it will take a time to explain it on the lecture, so I never show it on the lecture for 2D, but it has been done. And it's not terribly complicated, not too complicated.
Okay, I think we have to stop the discussion now, as the organizers told me. Let's thank the speaker again.
So let's just observe that we are 10 minutes late.